Today I am going to discuss about an important topic, corrosion. It is a natural process that converts the refined metal into a more chemically stable form. It can be an oxide, hydroxide, or sulfide. So you may ask, what is the main consequences of corrosion? So when corrosion happens at a material surface, it leads to gradual destruction. So the destruction can be mild or severe, mostly due to chemical or electrochemical reaction with the environment. Mostly the corrosion occurs at the metal surface. These are some of the examples of corrosion. The picture on your left, you can see the iron plate or the steel plate which is rusted, the most familiar example of corrosion. The second photograph represents the volcanic gases which have accelerated the corrosion in an abandoned mining machinery. The third photograph is the corrosion on exposed metal. You could see that the steel board appears very rough and several cracks appear on the steel surface. So these are the main consequences of corrosion. Mostly the cracks, the metal surface becomes rough. Now we will see the different types of corrosion and what are the reasons or how it occurs, the corrosion occurs. As you all know that noble metals like gold and platinum exist in nature in their combined forms. It can be oxide, it can be carbonate, hydroxycarbonate, sulfides, chlorides, and silicates. So when they extract these metals, they are reduced to the metallic states from their ores. Consequently, these isolated pure metals can be regarded in excited state, which means higher energy state than their corresponding ores. And they always have the tendency to revert back to the combined state, which is the lower energy state. So this is one of the reasons for corrosion. When metals are put into use in various forms, they are always exposed to certain environment. It can be a dry gas, moisture, liquid, etc. The exposed metal surface tend to decay, which means they are converted to the more stable metallic compounds, metal compounds. More or less, this process occurs very rapidly when they come in contact with the gaseous or liquid environment. So the environment can be gas or liquid. No matter it is gas or liquid, when a metal comes in contact with the environment, they tend to decay or the degradation is initiated. In other words, destruction or deterioration of the metal starts at the surface. Always the corrosion starts at the surface and then it proceeds further deep into the different layers of that metal. That means the depth can vary. It all depends on the environment and the nature of the environment and how strong corrosive the environment is. This type of metallic destruction may be due to direct chemical attack or electrochemical attack. So we can classify the corrosion into two types. One is direct chemical attack, the other one is electrochemical attack. In general, you can define corrosion as any process or deterioration or destruction and whatever the consequent loss of a solid metallic material through an unwanted chemical or electrochemical attack by its environment, starting at its surface. This is what it is called as corrosion. So the classical examples would be rusting of iron when exposed to the atmosphere. So the conditions may vary. A layer of reddish scale and powder of oxide can be formed and the iron becomes weak after corrosion or during the corrosion process. Sometimes a green film of basic carbonate, generally CuCO3 or a cuprous hydroxide or cupric carbonate, can be formed on the surface of copper when exposed to mixed air containing carbon dioxide. So these are some of the classical examples of corrosion. So now let's talk about the types of corrosion. There are two types of corrosion. One is dry or chemical corrosion and wet or electrochemical corrosion. So from the name itself, you can understand that dry means no moisture will be involved. So mainly this process or this type of corrosion occurs through the direct chemical action of the environment or atmospheric gases. This includes oxygen, hydrogen sulfide, SO2 with the metal surfaces. So main types of chemical corrosion: oxidation corrosion, corrosion by other gases, and liquid metal corrosion. Wet or electrochemical corrosion occurs by or occurs to when a conducting liquid is in contact with the metal. When two dissimilar metals or alloys come in contact, or either they are immersed or dipped partially in a solution, this type of corrosion can occur. To keep it simple, any metal surface when it comes in contact with the conducting liquid or water or electrolyte, then that leads to the formation of solid liquid interface, which can initiate the corrosion. So this type of corrosion is called wet electrochemical corrosion. The driving force can be a potential or a current or anything that leads to the formation of interface and also the activation or destruction of the interface. Dry or chemical corrosion, oxidation corrosion. As we discussed earlier in the earlier slide, the direct action of oxygen at low or high temperatures on metals, usually in the absence of moisture. This type of corrosion can occur at ordinary temperatures. In general, slight attack can happen. At low temperatures, this type of corrosion occurs with alkali metals like lithium, sodium, potassium, rubidium, etc. And not only it is limited to alkali metals, alkaline earth metals like beryllium, calcium, strontium, etc. can also undergo the corrosion, that is dry corrosion or chemical corrosion at low temperature. As a result of corrosion, they get rapidly oxidized. At high temperatures, or almost you can say all metals except the noble metals like silver, gold, platinum are readily oxidized and they lead to dry or chemical corrosion. So these are some of the classical reactions or the chemical reactions. You can call it as oxidation reaction, which lead to oxidation corrosion. In general, oxidation takes place at the surface of the metal, forming metal ion. So it's very simple chemical process, like metal on oxidation releases the electrons, n number of electrons will be released, and it leads to the change in the oxidation state corresponding to the number of electrons released, that is Mn plus species will be formed. The main process is loss of electron. The second type is oxygen can be converted to oxide ion, which is the anionic form due to the transfer of electrons from metal, which means oxygen will accept n number of electrons and it will be converted to the anionic form oxygen n minus. N minus corresponds to the number of electrons that is accepted by oxygen atom, gain of electrons. The overall reaction is of oxide ion reacts with metal ion to form the metal oxide film. So whenever the metal reacts with oxygen, a thin layer of metal oxide will be formed on the surface. This is the overall reaction which occurs when a metal is exposed to oxygen environment. Dry or chemical corrosion, corrosion by other gases, not only oxygen. The corrosion can be initiated or done by other gases like sulfur dioxide, carbon dioxide, chlorine, hydrogen sulfide, fluoride, etc. Fluorine gas, etc. The extent of corrosion effect entirely depends on the chemical affinity between the metal and the gas. The more the affinity is, the corrosion will be more. The degree of attack depends on the formation of protective or non-protective films. If the film form is protective or non-porous. Example, silver chloride film resulting from the attack of chlorine or silver. It depends on the intensity or extent of the attack. So when the intensity or extent of the attack decreases, because the film protects the metal from further attack. In the other case, if the film formed is non-protective or porous, the surface of the whole metal is gradually destroyed. So whenever the film is very thick and protective, the corrosion will be or the destruction will be very less. Whereas when a thick film is formed, the depending on the thickness, for example, it can be up to few microns to several microns thickness. So the protective layer thickness can vary. Whereas when the film is very thin and it can have certain pores on its surface, so through that pores the destruction can occur and the whole metal can be destroyed. Some classical examples are dry chlorine gas attack on tin can lead to the formation of volatile stannous chloride SnCl4, which volatilizes immediately, leaving the pressed metal surface for further attack. In petroleum industry, hydrogen sulfide will be, you know, the environment will be composed of hydrogen sulfide, and at high temperature it can attack the steel and form FES scales. It can form different layers or different thickness of FES scales, which can be porous and it can interfere with normal operation. So these are some of the real world examples of dry or chemical corrosion. Now let's talk about the liquid metal corrosion. Generally due to the chemical action of a flowing liquid. So we already discussed whenever a liquid comes in contact with the metal at high temperature, it can be the metal can be a solid metal or alloy, then liquid metal corrosion can occur. Such type of corrosion occurs in devices used for nuclear power, mostly in the nuclear power plant. Also, the corrosion reaction involves either dissolution of a solid metal by a liquid metal or internal penetration of the liquid metal into the solid metal. Whenever the metal is porous, then the liquid uh, metal can diffuse into the pores. Both these modes of corrosion cause weakening of the solid metal. Wet or electrochemical corrosion. Mostly this type of corrosion occurs when a conducting liquid, which is nothing but an electrolyte, comes in contact with the metal. In other words, two dissimilar metals or alloys, when they are immersed or dipped partially in a solution, then as I told before, metal liquid in contact, so junction it can form a solid liquid interface. That can also lead to corrosion. Particularly from the name, when you say electrochemical corrosion, you have to apply some electric field. It can be in the form of a potential. Once when you apply the potential to your electrode, then it initiate the flow of electron. As you know, that flow of electron contributes to the current between the anodic and cathodic areas. So depending on the voltage or potential you apply, so you can call the respective electrode as an or cathode. When you apply a positive bias, you can call it as an anode. When you apply negative voltage, you can call it as a cathode. It depends on the voltage or the potential difference. So the potential difference is the driving force for the electrons to move from one electrode to the other. For instance, from anode to cathode or vice versa. So the potential difference plays a major role in driving the electrons across the electrode interface through the external circuit. Let's talk about the anodic reaction, which involves the dissociation of a metal as corresponding metallic ions with the liberation of free electron occurs. For instance, anodic reaction means loss of electrons. So n number of electrons will be released on oxidation of the metal on applying some electrode potential. So this leads to the oxidation of the metal surface. So since n number of electrons are released, n number of cations will be generated at the metal surface. Emeritus, some for instance, if you take like metal like gold or platinum, for instance, gold, if 3 electrons are released, you will get gold. The classical example is stainless steel. So if 2 electrons are released, 2 plus charge. Remember that corrosion always occurs in anodic areas more rapidly than the cathodic areas. So now let's talk about the cathodic reaction. As you know, that cathodic reaction involves the reduction of proton and evolution of hydrogen. So the evolution of hydrogen is one classical example of a cathodic reaction. The other one, the type B, is about the adsorption of oxygen. It is nothing but oxygen reduction reaction. Anodic reaction. So the picture has been shown on the right. Both the mechanism of wet corrosion by hydrogen evolution and the mechanism of wet corrosion by oxygen absorption. In the anodic reaction, iron is oxidized to Fe2 plus state with the release of 2 electrons. Same time, cathodic reaction involves the reduction of proton, a 2 electron process. Since 2 electrons is released in the anodic side, 2 electrons will be consumed at the cathodic side and hydrogen will be evolved. It's a reduction process. Overall reaction, Fe plus 2H plus giving Fe2 plus plus hydrogen. Hydrogen is evolved. And here you can see the small cathodic area exposed. And anodic area, you can see this reaction happening, the cathodic reaction, 2H plus plus 2 electron avoiding hydrogen. And during this process, proton reduction will be happening. So diffusion of proton will toward the this metal surface will be cathode surface will be happening. The classical example is iron. And adsorption of oxygen, rusting of iron in neutral aqueous solution of electrolytes like sodium chloride in the presence of oxygen atmosphere. Anodic reaction is quite fast, like iron will be oxidized to Fe2 plus. And cathodic reaction, as you can see, that oxygen will be reduced to hydroxide ion in the aqueous electrolyte with the consumption of 2 electron process. The overall reaction will be Fe2 plus plus 2 OH minus forming iron hydroxide. So you can see the reaction has been illustrated on top, where the oxygen reduction, oxygen and 2 electron reduction process it formed with hydroxide ion. And as a result of the moisture presence and also the water presence, and rust will be formed on the surface, the oxide film will be there, and you can see the rusting, typical rusting behavior. Small anode area is caused by cracks in the oxide film where corrosion occurs. So whenever enough oxygen is present, ferrous hydroxide can be formed and it can be easily oxidized to ferric hydroxide, high valence hydroxide. So FeOH2 to FeOH3, yellow rust will be formed, and Fe2O3, yellow rust is nothing but Fe2O3 hydrated form. If the supply of oxygen is limited, the first case is enough oxygen present, the other one is supply of oxygen is limited. The corrosion product may be even black, and anhydrous magnetite Fe3O4 instead of Fe2O3, Fe3